Hi, this is Dr. Goldstein, and I'm going to be explaining some of the basic derivative rules. So the first one that we're going to look at is that the derivative of a linear function, mx plus b, just gives you your slope. So again, this mx plus b here, this is a linear function. And one way of thinking about why you just get the slope from a linear function as the derivative is that the derivative measures how much a function is changing. And when we're talking about a linear function, when we're talking about a straight line, the slope is exactly how much that line is changing. So again, this m is the slope, the literal slope of this line, which is how much the line is changing. And of course, you can also see that this is what you get when you use the limit derivative. I think I'll do that real quick over here. So if we take the limit as h goes to 0, and we do m times x plus h plus b, so that's that f of x plus h, minus mx plus b, so that's minus f of x divided by h. Well, the b's are going to cancel with each other. And then when we distribute that m, we get mx plus mh, and then we have minus mx over h. And so the mx's cancel with each other. And now we have the limit as h goes to 0, mh over h, and now our h's cancel. And you can see you just get the limit of m, which is just m. So there's a couple of different ways of seeing why this rule is true. On the intuitive side, the derivative is the measure of how much a line is changing, and that's measured by its slope. And then on the computational side, we can use the limit as h goes to 0 definition. Okay, so here's some actual concrete examples of using this rule. If I want to take the derivative of the linear function 5x plus 2, I just get 5. Because I can look at that and see, okay, m is 5. In another example, if I want to take the derivative of 4 minus 1/2 x, if you can look at that and spot the m, you can just pull it out, but we can also rewrite it as minus 1/2 x plus 4, and then we can see, okay, yeah, that's mx plus b, and the m in this case is minus 1/2. Two more examples. The derivative of x, again, if you want to be very, very thorough, you can write this as 1 times x plus 0. So here we have that m is equal to 1 and b is 0. And so when we take the derivative of x, we just get 1. And likewise, we can rewrite 7 in the form mx plus b, writing it as 0 times x plus 7. So here, m is 0 and b is 7. And so when we take the derivative of this, we get 0. So again, going back to our intuitive idea of the derivative being 0, this means that the function f of x equals 7 doesn't change. Remember, the derivative is how much our function changes, and so what we're saying is that our function does not change. And that makes sense because f of x equals 7 is a constant function. So this makes sense for a constant function. Yeah, this function does not change. And if you would like, I can graph this function quickly for you. So here's my x-axis and my y-axis. And if this is the value 7 right here, then f of x equals 7 is this line right here. So this is f of x equals 7. And you look at that and you say, yep, yeah, that function doesn't change. It stays the same all the way across. Okay, so that is our first derivative rule. here is another one for you. This one I'm not going to explain anywhere near as thoroughly because it's much, much harder. I'm sure that you can find a proof of it either in a book or online if you want to. For any non-zero rational number k, if my function is this power function x to the k, I can take the derivative of that by taking that fat power and putting it out front and then lowering the power by 1. So the way that I like to summarize this rule when I'm talking about it with people is that the power comes down and then you subtract 1 from that power. So let's look at a couple examples of this. If we are taking the derivative of x squared, in this problem k is 2. So when I bring that out front, I have 2x to the 2 minus 1. And so I have 2x to the first power, and we don't usually write x to the first power. We usually just write x. So the derivative of x squared is 2x. And I'm guessing that you've probably seen this using the limit definition of the derivative before, so hopefully that's not super surprising to you. You've probably also seen the second one. If you take the derivative of x cubed, again, you bring the power down front, and then you subtract 1 from the power, so we have 3x squared. So again, in the first problem, your k is equal to 2, and in the second problem, your k is equal to 3. Okay, if we look at the third example here, the derivative of the square root of x, we have to remember that the square root of x can also be written as x to the 1/2. So here our k is 1/2, and when I bring that out front, there we go, there's 1/2, and then I have to subtract 1 from the power, and 1/2 minus 1 is negative 1/2, so I end up getting 1/2 x to the minus 1/2, which is correct, but it's not very understandable, and we probably want to write this in a form that we can actually work with. So remember, a negative exponent means that you use the reciprocal, so I have 1 over 2x to the 1/2. That x to the 1/2 comes down to the denominator, and then why not, we'll go the extra little bit and actually write that as the square root of x. So again, this is another one that you can compute using the limit as h goes to 0. You've probably seen this example before. I know I always do this one in class. But in this rule, you're really just using the fact that k is equal to 1/2, and then you're rewriting some exponents to make it a little bit more understandable. Okay, the last example that I'll do with this particular one, if you're taking the derivative of 1 over x squared, again, remember that negative exponents let you rewrite fractions. 1 over x squared is the same as x to the negative 2. And so now my k is equal to negative 2. I bring that down. And then I have x to the minus 2 minus 1. Minus 2 minus 1. I always have to subtract 1 from the power. And so what happens here is something that's a little bit weird. It looks like my power goes up. I mean, it went from minus 2 to minus 3, so that's down. But now when I rewrite this, getting rid of the negative exponent, rewriting it as minus 2 over x cubed, it looks like my power goes up. But again, you just have to remember that powers in the denominator are negative, and so when they go down by 1, they're getting more negative, which means negative 2 is going to go to minus 3. So in this last example, we have k equal to negative 2. So this rule you can use for any exponent k as long as it's either a whole number or a fraction. Okay, here are 2 more rules for you. These are the constant multiple rule and the sum rules. So here, k is any constant. F and g are functions that are differentiable, meaning we can take their derivative. if I have k times some function and I want to take the derivative, I can pull the k outside of that and just take the derivative of the function and multiply it. So constants can come outside of the derivative. Similarly, if I'm taking the derivative of a sum, I can essentially distribute the derivative over my sum. The derivative of a sum is the sum of the derivatives. So both of these two rules together tell us that the derivative is linear. That's another way of saying this. So taking the derivative is a linear operation, meaning it distributes over addition and you can pull constant multiples outside of it. So this is just another phrasing that you're likely to see, that the derivative is linear. So let's apply these two rules along with the last rule to one example. So first, when I'm taking the derivative of 7x cubed minus x to the 6th, I want to use rule 4. I'm using rule 4 to break this up as the derivative of 7x cubed plus the derivative of negative x to the 6th. So here I'm remembering that subtraction is the same as adding minus 1 times something. So now I can use, once I've split up the addition, I can use rule 3 to pull the constants out. So I have 7 times the derivative of x cubed, and then this negative sign comes out. Again, I'm just pulling these coefficients out. So now I have minus the derivative of x to the 6th. And now I can use my rule from the previous slide, the power rule. And when I take the derivative of x cubed, I pull down the 3, and I subtract 1 from the exponent. And now when I take the derivative of x to the 6th, I pull the 6 down, and I subtract 1 from the exponent. And so when I simplify and I actually do this multiplication, I end up getting 21 x squared minus 6 x to the 5th. And again, you can do this one with that limit as h goes to 0 definition, but I'm betting you really don't want to. So again, the first step here, I'm using rule 4 to split up my sum. I'm pulling my constants out in my second step using rule 3, and then in my last step, I'm using rule 2 to actually take the derivatives of the functions x cubed and x to the 6th. So sometimes you will see another rule called the difference rule, which I've technically used here, which is that the derivative of f of x minus g of x is the derivative of f of x minus the derivative of g of x. But really, that's just a combination of rules 3 and 4 here. So I prefer not to list it, just because I don't like to keep too many rules in my head. Okay, so those are our 4 basic derivative rules. I'm going to do one more example that shows you everything that we just talked about all in one go. So here I'm going to take the derivative of this fraction 1 plus root x divided by x. So you might look at this and you might say, but I can't use any of my rules. I don't just have a power of x. I have no constants that I can pull out. I don't even have a sum that I can split up. So I look at this fraction and I say, well, what can I do? Well, I can split it up over the denominator. So I can just rewrite the inside as 1 over x plus root x over x. And now remember here, this root x over x, this is x to the 1/2 over x to the 1, and so I can write this as x to the minus 1/2. And also, because we're going to be taking derivatives, remember that 1 over x is the same as x to the minus 1. So having established that, now we have a sum that we can split up. So I have the derivative of x to the minus 1 plus the derivative of x to the minus 1/2. And I've done two types of algebraic simplification. I split my fraction up over the denominator, and I've rewritten everything just in terms of rational powers of a variable. So in this step right here, I used rule number 4. But other than that, I've really just done algebra. Okay, in my next step, I'm actually going to take derivatives. I'm going to bring that minus 1 down. So I have that minus 1. I have to subtract 1 from my exponent. And then in my next term, okay, I have to bring down that minus 1/2. And then I have, okay, x to the minus 1/2 minus 1. So here I'm using rule 3. And notice that this is actually from here to here. This is where I'm actually taking a derivative. So if you're wondering, where did that d dx go? That was me actually using rule 3 to take the derivative. Okay. Sorry, that wasn't rule 3. That was rule 2. Oh, that was the power rule. That was rule number 2. Okay. So the last thing I'm going to do is actually rewrite this in an understandable way. And again, this is just algebra. So I have negative x to the minus 2 minus 1/2 x to the minus 3/2. I'll do this in 2 steps so that it makes a little bit more sense. I have this negative out front, and then x to the minus 2 means 1 over x squared. And then I have a negative second term as well. The 2 is in the denominator, and the negative exponent on that x means that I put that in the denominator as well. And this is fine, except you may or may not look at that x to the 3/2 and say, oh my goodness, what is that? So I'll rewrite this one more time, the most understandable way. And that second term is 2, that is the square root of x cubed. So again, both of these are really, they're the same thing. They're both equally correct. And depending on what you want to do with it, you might prefer one over the other. The last one is certainly the most understandable in terms of computing a value if you're going to plug something in. But that second to last one, or even the step before this, if you want to compute another derivative, let's say you want to compute the second derivative or the third derivative, whatever, you actually might not want to simplify. So again, the final form of your derivative is going to depend on what you'd want to do with it, but there's a lot of ways of writing these things. Okay, so those are your basic derivative rules. We have the derivative of a linear function. Here we have a nice summary. We have the derivative of a linear function, mx plus b is just m. And one thing that we looked at as an example is that the derivative of a constant is 0, because that's the case when m is equal to 0 in mx plus b. We have the power rule. The derivative of x to the k is kx to the k minus 1. You pull down the power, you subtract 1 from the exponent. The derivative of a constant times a function is the constant times the derivative. You can just pull the coefficient out front. And the last one, the derivative of a sum is the sum of the derivatives. You can distribute the derivative over sums.